In previous video, we introduced conditional probability. In this video, we are going to build Bayes' theorem step by step, starting from ideas you already understand. The key message of this lecture is Bayes' theorem is not a new formula to memorize. It is a way of reasoning using conditional probability and the total probability rule. Here is a plan for this video. First, we will start with the example from our own class to motivate the kind of questions Bayes' theorem answers. Then we will review the total probability rules, followed by the engineering contamination example. After that, we will introduce Bayes' theorem and finally apply it to the medical example involving blood pressure. Let's begin with the example from this course. I am going to define you two events. Events A. Events A is the events that students earn A in the course. Events B is the events that a student is a biomedical engineering major. So now here is the key question. If a student earn an A, what is the probability that the student is a biomedical engineering major? Mathematically, this is written as this probability of B given A, that is the probability of student earn A in this course given the student is a biomedical engineering major. So then it is asking among the students who got A, where did they come from? So this is not asking how many biomedical engineering students gets A's. So this type of question is exactly what Bayes' theorem is designed to answer. Before we use the Bayes' theorem, we need the total probability rule. Let's continue using the class example. Let A be the events that the students earn A, and let B be the events that the students is biomedical engineering major. So then every A in the class must come from one of two groups. So it can be biomedical major students or non-biomedical major students. So then we can partition in our population of the class students. Population, that means class students to two parts. I will divide for its B and complement non-biomedical engineering major students. That's mean complement of BC, or you can write if you want the prime of B. So then the new events on the population, assuming this is your new event, it's A. So I'm going to express the probability of A using the B and complement of B. So if you see that, I will divide for the intercept this area. That's mean I can write intercept of B and A. You can write as the intercept notation. So that's mean set. We can draw the other area, this area, because we need to write the probability of A using these two partitioning. So this part, this is we can write as the complement of BC and A. So then let's write our probability of A equal probability of, or you can write first like this. A is the area of the circle. We can write B, A, or A intersect B. It doesn't matter. Union. That's when we have to add with the other part, other area of the part, and BC intercept A. So then my goal to get the probability of A, then we have to find the probability of B or A intercept plus, because we are quantifying the measure now, probability of B. A. Either way is fine. You can replace B, A plus probability of A intercept BC. Both ways fine. So then we using the multiplication rule of the probability, so we can express probability of A intersect B as, you can start from probability of A. So I will write first here. So which formation is it's the we can write here. So then probability of A intersect B, you can write 2 pound. If you start from A, probability of A, then B given A, or probability of B, probability of B given A. So which way we have to use this? This is the two expressions are same. So but our goal to get probability of A, we don't know this exactly. So that's mean we have to use this one. Then we can express this one, probability of A equal probability of B times probability of A given B plus this one B, also we can write probability of complement of B times probability of complement of B given probability of A. So this is we call the total probability rule. So you will see that it's we express here. So this formula is not the Bayes theorem yet, but it will become the denominator of the Bayes theorem later. Now let's look at the engineering example. Suppose semiconductor chips can be exposed to high contamination or not high contamination. So here is a probability that the events that contamination is high. So then assuming let F be the event that the product fail and the H be the event that contamination is high. This means here the probability of level 0.2 mean it's, we can write this one as a probability of its events that contain is high is, and here is not high. That's mean the complement of high. So failure can occur in two different ways, under high contaminations or under not high contamination. That's mean this is point 1 means probability of failure under high contamination. This is meaning probability of failure not high contamination. That's mean complement of H of C. So then this structure should already look familiar. This is total probability. Using total probability rule, we can write probability of F because it's our question is find the probability of F. So you can express, maybe first I can think, okay, I know that it's this is event already. Maybe I will like as correctly, a little bit similar to the correctly area. H, C, the new events. Let's get the red color. New events is failure. So then, like previously, you can draw this. So we can write probability of F probability of F intersects H plus probability of F intersect H complement. So then these two we have to express as a probability, conditional probability. So if I do, maybe I can start from H intersect B as H or probability of F given H. But we know that we can't go this way. Why? Because this is our goal in order to find our probability. So this is not work. So then this meaning we have to start from H, probability of H given F. So we see that these probability already our informations from this question. So and also in here second part we can probability of C, then C equals to given. So either method you can change, or I like to write this way. It's up to you. So then we can directly substitute the value of the probabilities. These probabilities, probability of H is 0.2 and probability of F given H is 0.1 plus probability of H complement is 0.8 times 0.005. So then we can find this value point. You can calculate 0, so 0.2 plus 0.804 004, right? And then add together 0.02. So this is the probability of product failure. It's very less. So let me check this again. You can check it from the calculator. Oh, yeah, check it. It's 8 times 440. That's mean 40. So we have to keep the 4 decimal. Yeah, this is correct. So then this is the total probability for the product failure. In general, Bayes theorem works with the partition of the sample space. So assuming in here E1, E2, E3, E4, it's your sample space is partition. I will write here draw 2. This is our population. We divide for mutually exclusive events. Then events, and this is P. Then you will see that we can get we express this event B as these 4 areas, and this, and also this black area, and also the color, this area. So I will write here probability of, let's first write, compare the areas. B is, this is A1, A2, A3, A4. A1 union A2 union A3 union A4. So that's mean how we can get the A1 B equal A1 is B intersect with B E1, then union E2 intersect with B, and union E3 intersect B, and union E4 intersects B. So that's mean if you want to write the probability notation, so probability of B equal probability of E1 intersect B plus probability of E2 intersect B and plus probability of E3 intersect B plus probability of E4 intersect B. So same way how we express the HR part, as a conditional probability, we can start with BE1, probability of E1 given B. So then I will write one more, E2, probability of E2 given B. So same way you can express each of these measures. Then this is meaning summation. So that's why we express the probability of B. We can write summation of E1 to E4 K if you have K events, and probability of EI, and instead of 2 EI and B. So this is total probability rule for the general case. This formula used in order to derive the Bayes theorem. So if you want to find the probability of B greater than A given B, we can write using the conditional probability of A intersect B divided by probability of B. And this one using, again, multiplication rule, you can express this way. So in order to express probability of B, we can use the total probability rule. So assuming if you have E1 to Ek are mutually exclusive and exhaustive, and also probability of B greater than 0, then you can write, I will first write as a E1 given means probability of E1 intersect B divided by probability of B. This part we can use these expressions, total probability rule. Then we write this, and top part using the condition probability. We can write this on two ways, probability of E1, probability of E1 given B, or probability of B, but we can see that it's O, probability of B given E1. But this is similar, so that's mean we don't use this format, only this way, divide by probability of B. So this is the Bayes theorem. Now here the total probability of observing B, this formula will appear many times throughout this course. Now let's apply Bayes theorem to health-related example. Define the events H, the person has high blood pressure, and O, the events that person is overweight. The question is here, if a person has high blood pressure, what is the probability that they are overweight? That is, you can express as mathematically as a probability notation, probability of O given H, probability of a person has high blood pressure given the person is overweight. So be careful that this is not the same as a probability of high blood pressure given overweight. To make the calculations clear, suppose we observe 100 people, 40 is overweight, from overweight person 20 with the high blood pressure, and 60 not overweight, from not overweight people 10 with high blood pressure. Let's convert this statement as a probability notations. So first we have a 60 out of 100 is overweight. We know the events. The person is overweight, we represent as symbolize as the O, probability of overweight, O equal 40 out of 100, that's mean 0.4. Probability of not overweight persons, that's mean complement of OC, 60 out of 100, 0.6. And the 20 is if the person is overweight, that's mean from 40, 20 is with high blood pressure. That's mean probability of, if overweight, it's high blood pressure. It's 20 out of 40. That's mean 0.5. And next, if it's not, the person is overweight, that's mean from 60, 10 is high blood pressure, having high blood pressure. Probability of not overweight complement of O, it's having high blood pressure. 10 out of 60. 1, 6. Then we can directly substitute this value for these equations. This is our goal. Finally, find, I will write down again, probability of given person is high blood pressure if overweight. So how we can find? We can write this on probability of O intersect H divided by probability H. Then we can express this one as the condition probability of O time probability of H given O divide by, we have only 2 of H, that's mean high blood pressure. So we can divide like this. If it's high blood pressure, not high blood pressure, it's oh no, this is the next event. It's overweight, not overweight, then high blood pressure H. We can express this one as a probability of O intersect H plus probability of O complement and H. So then each of this we can represent probability of O, H, O. So again we are writing as probability of O, probability of H given O plus probability of O complement time probability of H given OC. Then each values we can substitute to this expression. So then P of O is 0.4 times O given H 0.5 divided by same 0.4 times 0.5 plus then 0.6 times probability of O complement given H 1/6. This means 0.1. So then we can simplify this. Finally, 0.4 times 0.5 divided by, this is when you multiply 0.2, this is 0.1, we can write as a 0.3. Finally, 0.2 divided by 0.3, mean 2/3. So that's mean if the person is overweight, probability of overweight, it's the person having high blood pressure is 2/3. Let's notice something important here. So then this results, that's mean given overweight, only 50%, given only 50% have high blood pressure. But given high blood pressure, about 2/3, 67% are overweight. That's mean one people is overweight. That's mean he has a chance of getting high blood pressure 50%. And but if the one person having high blood pressure, that means 67% has a chance of getting overweight. Bayes theorem is what connect them correctly. So this idea appear later in medical testing, harvest testing, engineering diagnostics, and data science and machine learning engineering. Let us summarize. The Bayes theorem allows us to compute the probability of a case given and observe outcomes by combining prior probabilities, condition probabilities, and the total probability rule. The next lecture, we will move on the random variable, but the reasoning from today will continue to appear throughout the course. Thank you.